I'm Hope Allen, DriveWorks Product Manager, and I'm here with Aradia Nara, Senior Solutions Architect for Autonomous Vehicles, and we are here today to explain how to integrate automotive sensors into DriveWorks. This integration, which is enabled through what we call sensor plugins, allows your sensors to be seamlessly used with the rest of the NVIDIA Drive software stack with minimal development effort. We explore this topic from all sides, so regardless if you're a sensor manufacturer or an autonomous vehicle application developer, we will explain the necessary steps to get started. We have a pretty full agenda for you today. We start out with an overview of the NVIDIA Drive platform, which includes state-of-the-art hardware and software for autonomous vehicles. We then focus on the NVIDIA DriveWorks SDK, a middleware SDK for autonomous vehicle software development. The DriveWorks sensor abstraction layer is the doorway into Drive software because it generalizes sensor interfaces and therefore reduces the need for custom code to integrate a new sensor into your application. In order to scale with the growing autonomous vehicle market, the DriveWorks sensor abstraction layer allows sensor manufacturers and AV developers to integrate and use their own automotive sensors with the NVIDIA Drive platform. In today's webinar, we will cover how to do this sensor integration and also provide a demonstration of this feature in action. NVIDIA Drive is an open, scalable, and modular end-to-end platform for autonomous vehicle development. By tackling the entire end-to-end pipeline, we ensure that we are providing a coherent and integrated solution to this industry's biggest challenges. Drive includes the data collection and infrastructure for large-scale deep neural network training, as well as a platform for bit-accurate hardware-in-the-loop testing. Additionally, Drive provides the hardware for high-performance, low-power in-vehicle processing and a complete software solution that includes SDKs for the development of autonomous driving and in-cabin monitoring applications, a high-fidelity simulation for software validation, as well as advanced applications that demonstrate our capabilities. The NVIDIA Drive platform is open. We expose our software APIs and a wealth of info about our hardware and software. It is modular, meaning you can integrate the pieces of our solution into your own with relative ease. Finally, it is scalable, so you can use as much or as little of our platform as you need. We built the platform following these precepts because we want to advance the AV ecosystem and allow all developers to build on top of it. In this, our solution is unique. Our goal is to have every developer in the autonomous vehicle industry using the Drive platform. The Drive platform supports developers in segments that include Tier 1s, OEMs, mapping companies, sensor manufacturers, AV startups, education and research institutions, and many more. We offer a global solution. For example, we are training our neural networks to detect signs and lights all over the world, including North America, Asia, and Europe. There is something here for each one of your use cases. So how do you get started with Drive? Well, we have 3 entry points for developing on the NVIDIA Drive platform. First is the NVIDIA Drive AGX Dev Kit, which includes an NVIDIA Drive AGX Xavier or Pegasus computer, as well as NVIDIA's Drive software. Drive software includes SDKs that enable you to develop autonomous vehicle applications for your specific use cases. If a more complete solution is desired, Drive Hyperion is a reference architecture that consists of a complete sensor suite, computing platform, and our full software stack for autonomous driving, driver monitoring, and visualization. Drive Hyperion can be integrated into a test vehicle, enabling developers to develop, evaluate, and validate AV technology. Finally, NVIDIA Drive Constellation is a full hardware-in-the-loop, end-to-end simulation platform that developers will have access to in the near future to help develop and validate their own AV stacks. Let's focus on the NVIDIA Drive AGX Dev Kit for a moment. The Drive AGX Dev Kit provides the hardware, software, tools, and sample apps to get started on the development of production-level autonomous vehicles. It is suitable for all AV developers that require an auto-grade computing platform that meets safety standards, is compliant with key regulatory requirements, and has a thriving ecosystem of automotive partners. The Dev Kit includes a Drive AGX computer, along with a vehicle harness to connect the platform to the car, an international power supply, a camera sensor, as well as other accessories. The Dev Kit also includes Drive software, which is our open end-to-end in-vehicle software solution. Drive software features libraries, toolkits, frameworks, and compilers for vehicle manufacturers and suppliers to develop applications for autonomous driving and user experience. Digging deeper into the Drive AGX hardware, you'll find an architecture that balances performance, safety, and power consumption. All NVIDIA Drive AGX platforms are built on top of the same Xavier system on a chip, which is the world's first processor designed for autonomous driving. DriveAGX includes 2 Xavier SoCs that each have 6 different types of hardware engines for redundancy and for optimization of the overall processing load. The platforms also include interfaces for integration with the vehicle and its sensors. We provide 2 versions of the DriveAGX platform that leverage the Xavier SoC. The first is DriveAGX Xavier for Level 2 and Level 3 driving, and the second is DriveAGX Pegasus for Level 4 and higher applications. The Pegasus platform includes 2 Turing discrete GPUs for running algorithms that need extra compute power. On the software side, NVIDIA Drive Software is our open and complete solution for autonomous vehicle software development. It harnesses the DriveAGX platform to enable capabilities that meet the performance demands of safety-critical applications. The scalability and modularity goals of Drive Software enable developers to efficiently use as much or as little of our stack as is needed for their use cases. In more detail, DriveOS is the foundational layer of the software stack, consisting, among other things, of an embedded real-time operating system, a hypervisor, NVIDIA CUDA libraries, and NVIDIA TensorRT. At the upper layers, DriveAV provides advanced high-level autonomous vehicle capabilities, including robust obstacle and path perception, localization, and planning. DriveIX is our solution for in-cabin assistance, such as driver monitoring and visualization. In the middle, and at the core of this webinar, is the NVIDIA DriveWorks SDK. DriveWorks enables developers to implement autonomous driving solutions by providing an exhaustive library of software modules that leverage the computing power of the DriveAGX platform, as well as a collection of sample applications and tools to assist with software development. DriveWorks is the entry point into the overall Drive ecosystem. Let's go more in depth into DriveWorks. DriveWorks is the foundation for autonomous vehicle software development. DriveWorks is modular, open, and designed to be compliant with automotive industry software standards such as ISO 26262 and MISRA-C. This gives you a production-ready, stable platform while still supporting rapid AV software development. This modularity, along with an extensive catalog of optimized algorithmic modules, enables developers to quickly integrate their code with DriveWorks while still giving flexibility and control over their applications. Included in each DriveWorks release are tools that make it easy to develop on the Drive platform, including support for recording sensor data and calibrating the vehicle's sensors. Additionally, the SDK provides detailed documentation that covers our APIs, guidelines, and workflows. We also include a large number of code samples to get you started as quickly as possible and increase productivity. DriveWorks allows developers to focus on developing autonomous vehicle applications instead of spending time on implementing low-level functionality and infrastructure. Finally, DriveWorks supports a large ecosystem of sensors that's constantly expanding with new sensor models, and features. If you integrate your sensor with DriveWorks, then you're making it available to all of the other developers using Drive. DriveWorks is designed to expose the full potential of Xavier to developers. The Xavier SoC has different hardware engines to accelerate the diverse computational loads demanded by AV applications. Let's do a quick rundown on Xavier's hardware engines. The Deep Learning Accelerator speeds up deep neural network inference. The Programmable Vision Accelerator drives computer vision and point cloud processing applications, while the Image Signal Processor and Multimedia Codecs accelerate image processing. Finally, the GPUs and multi-core CPUs accelerate general autonomous vehicle software. To expose this computing power to developers, DriveWorks provides the framework and constructs to efficiently communicate and command the execution of the many processors inside Xavier. Additionally, the DriveWorks algorithm modules use the most efficient algorithms and have also been optimized to run on their intended hardware engines. Many of these modules have multi-engine backends, which means you can control which engine you want to run your code on. Finally, DriveWorks follows rigorous design principles, including the minimization of memory copies and efficient data communication between the hardware engines, just to name a few. Focusing on DriveWorks just a bit further, you'll find that it comprises 3 major functional areas: Drive Core, Drive Calibration, and Drive Networks. Drive Core contains the modules and tools needed to acquire and process sensor data, interface with the vehicles, and perform other low-level functions. Drive Calibration contains the modules and tools needed to measure and correct sensor calibration parameters, as well as modules for modeling and estimating the vehicle's motion. Drive Networks contains numerous fully trained deep neural networks to perceive obstacles, drivable paths, and what we call wait conditions, which are situations that require the vehicle to stop or slow down. Each DriveWorks release contains all of these capabilities and are further refined and expanded upon in each new release. Let's dive into some of the key DriveWorks features. DriveCore includes an ever-expanding collection of accelerated algorithmic modules for computer vision and point cloud processing. These are common algorithms. For example, we provide image processing modules for feature detection and tracking, rectification, structure for motion, and many more. On the point cloud processing side, DriveWorks has modules that include point cloud accumulation, registration, and segmentation. Additional capabilities are provided in each release. The major benefits of using the DriveWorks modules are that they are designed to be modular and open, making them easy to integrate. The modules also abstract away the details of the underlying drive hardware engines and sensor specifics, making it easy to develop optimized and complex applications. The inputs to these modules are the generalized DriveWorks sensor abstraction layer data structures. The sensor plugins are designed to output the data structures that these modules expect, so sensor plugin users can start using the DriveWorks modules right away. DriveCore also includes a suite of recording and replay tools to assist with software development. The recording tool allows you to simultaneously capture high-quality sensor data from the multiple sensors and devices on your vehicle. When played back through the DriveWorks sensor abstraction layer, the recording data will be synchronized and calibrated as it was in the vehicle. This is useful for training DNNs and basically all other development use cases. We provide additional offline tools for post-processing your data recordings, such as recording validation, clipping of large data files, and format conversion tools. These tools make it easier to handle and use your recordings. Sensors that are compatible with the DriveWorks sensor abstraction layer can automatically be recorded with the DriveWorks recording tool, which is another benefit of using the sensor plugins. Included in Drive Calibration are a collection of tools and modules to assist with measuring and correcting the vehicle's sensor position and additional intrinsic properties. The static calibration tools provide ground truth for the autonomous vehicle sensors, and the self-calibration modules can be used in the vehicle for real-time corrections of the nominal parameters caused by environmental changes or mechanical stress. As with the other DriveWorks modules and tools, Drive Calibration software is compatible with the DriveWorks sensor abstraction layer, so sensor plugin users can use their capabilities to calibrate their sensors instead of developing their own, which can be very time-consuming. We also provide drive networks with each DriveWorks release. Included are a catalog of fully trained deep neural networks that provide advanced capabilities for autonomous vehicle solutions. Leveraging the company's deep learning expertise, NVIDIA has invested in extensive data collection, labeling, and optimization to train highly accurate networks for AV applications. We have DNNs for obstacle detection and classification, path perception, weight condition perception, and more. In case you have your own DNN that you'd like to run on the Drive platform, DriveWorks also provides support for managing the overall lifecycle of a DNN. Specifically, DriveWorks provides support for performing inference on models that have been optimized using NVIDIA's TensorRT. This inference can be run on Drive's GPUs or its deep learning accelerator engines. Before we go too far, I'd like to walk you through our recommended workflow for Drive software development. All work begins on your host development environment, which is an x86 PC running Ubuntu. When you're ready to test on the Drive embedded platform, we provide the capabilities to cross-compile your software for the target. We also provide tools for debugging and profiling to improve performance on the Drive platform. This workflow ultimately prepares you to deploy your software on vehicles in the real world and continue testing. Feedback loops along the way enable you to gather valuable insight from testing at your desk, on the bench, and in the field, allowing you to continuously improve your application and thus achieve your production goals. That was a quick introduction to the Drive ecosystem and the DriveWorks SDK. Let me pass the presentation over to Aradia so she can dive deeper into the DriveWorks sensor abstraction layer and the sensor plugins.
Thank you, Hope, for that great introduction. Now, we're going to dive a little deeper into what I think is one of the most useful aspects of DriveWorks, sensor abstraction layer and plugins. This is going to be the entry point for all the sensors into NVIDIA Drive software stack. There are two main principles behind the SAL and the plugins. First is to provide a unified interface to manage the lifecycle and use of sensors such as creation, destruction, and gathering of data. And the second is to provide common data structures and transport layer abstractions that hide the variations between different sensor devices. We provide mechanisms to serialize raw data of the sensor with no modifications. So if you do need to play back the data at a later time, you're able to still retain the original data of the sensor. Once you have this recorded file, DriveWorks gives you the capability to replay the file as a virtual sensor. Whether the data is coming from a live or virtual sensor, it will behave similarly to the upper layers of the software stack. All you have to do is switch between live or virtual by just changing one parameter. So to all the upstream applications, both paths are identical. This is extremely useful when you're trying to debug your application in an offline environment. Usually when we record data from all sensors, it's often desirable to skip to different time regions within the session. The DriveWorks sensor stack provides seeking capability which allows a user to move between different time regions in the recording. Once integrated to the DriveWorks SAL, all sensor outputs map to a set of data structures that are common throughout the whole stack. This creates a nice hardware abstraction layer so that the application developers can focus on solving problems they care about without worrying about sensor integration. We have inbuilt support for all sensors like lidars, radars, camera, IMU, and GPS. Any sensor that is integrated into DriveWorks SAL will have three phases in their life cycle: initialization, runtime, and release. The initialization phase is where the sensor is created, and the release phase is where it is released. The APIs that the application developer needs to call are the create sensor and release sensor. Create sensor is where transport layer is opened, memory allocations happen, and all the FIFOs are pre-allocated. You finish the creation step when the sensor is alive and the memory is allocated for it. Release sensor deallocates this memory, clears all the pointers, and closes the transport layer. During the runtime phase, the data consumption begins with the DW sensor start and ends with DW sensor stop. These are very lightweight start and stop calls. The idea is to start and stop the sensor without destroying the sensor itself. In some of the sensors, this lightweight start and stop are supported by default, and in some you can mimic this by starting and stopping the data to the application layer. To the application, it looks as though the sensor stopped and started again. The reason to do this is so that you can start the sensor again with minimal latency. One of the biggest challenges of working with sensors is getting time-stamped and synchronized data. DriveWorks provides tools and techniques to achieve this. For all our sensors, DriveWorks timestamps sensor data using an internal SoC clock at reception time. If the sensor you're working with additionally provides a native sensor timestamp, we record this timestamp as well. Generally, the host reception timestamp will carry a channel latency as shown in this slide. This can be calibrated to some extent, but the latency will exist regardless of the system. To avoid this latency, DriveWorks provides a time synchronization mechanism to convert a sensor timestamp from certain domain into the default SoC clock domain. For sensors that have totally uncorrelated time clocks and that provide a sensor timestamp, we can use a moving average of the timestamp deltas to smooth the time. While this doesn't remove any channel latency, it's helpful for cutting out jitter due to CPU thread scheduling on the receiver side. For sensors that can be synchronized via PTP, we can make Xavier to be the PTP master and have all the sensors synchronized to the host time domain. Other sensors, especially lidars, can make use of an external GPS and/or PPS signal to sync and time their measurements and provide UTC sensor timestamps. This same data, mirrored on the SoC, will allow for conversion of sensor timestamps in the UTC domain to the internal SoC time base. For every PPS pulse received on the GPIO, DriveWorks records a tuple containing host time, PTP time, and the UTC time. This continuous equivalence table allows us to convert between any one of these time domains. Switching over to the memory model side of things, all sensors integrated into the DriveWorks SAL have pre-allocated FIFOs. The create sensor call pre-allocates this. We avoid runtime allocations and maximize the performance by avoiding the copy of the data by creating these pre-allocated pools and providing direct access to the application. We achieve this mainly through ownership transfer model. You collect the data into a FIFO stack, you provide a pointer to the application, and the application needs to return the pointer to you when it's done. All the capabilities that were mentioned so far are readily available for you to take advantage of. And the way to do that is to integrate your sensor into the sensor abstraction layer by implementing plugins. We have two different flavors of plugins: custom camera feature to integrate GMSL-based cameras into the DriveWorks SAL, and the sensor plugin framework for all the other sensors. Let's look into how to integrate custom cameras. Before integrating custom cameras into the DriveWorks sensor abstraction layer, there are certain assumptions that need to be satisfied. First, whatever custom camera module that you're using has to be compatible with the serializer and the deserializer combination on the board. We recommend using GMSL2, and the model numbers are Maxim9295 and Maxim96712. The custom camera feature, however, is also compatible with GMSL1, Maxim96705 and 96712 combination. Custom camera relies on NVIDIA SAL library, so you will need to have a vendor-provided SAL library file for the camera you plan to use. Once you get this file from the vendor, you integrate the GMSL camera APIs, and then you integrate into the DriveWorks sensor abstraction layer. Once the integration is done at the SAL layer, the integration into DriveWorks is pretty straightforward. We just have to specify the config parameters in the parameter string, and these are the parameters that need to be specified. Mode represents whether the camera is in master or a slave mode. Slave mode is required when Xavier B is trying to access the camera, which is currently being used by Xavier A. Camera name is the name of the camera module that is specified in the SAL library. PSI port is the identifier of the port to which the camera module is connected, and the num parameter signifies the number of cameras connected. For non-camera sensors, you can use our sensor plugin framework. With this framework, you're responsible for providing implementations for most of the sensor functionality. You own the communication channel, the life cycle of the sensor, and the data decoding. Once implemented, DriveWorks provides the infrastructure, the data structures to interface with, recorder, and playback tools. You have the vendor-provided library file, which implements the custom control and data plane for your sensor. Once you implement the required API calls, it's very easy to integrate to the SAL to take advantage of the entire DriveWorks stack. Because the sensor abstraction layer is a unified interface, application developers would not have to worry about sensor-specific details. It is very easy to integrate a custom sensor into the SAL using this plugin framework. There are 3 integration steps followed by an additional 3 steps to start receiving data. After the required sensor APIs are implemented by following the recommended design principles, such as no dynamic memory allocation, no thread spawning, etc., the next step is to compile the plugin as a shared object file. This .so file is shared with app developers who can then begin to read data from the sensor. As an application developer, once you receive the SO file, to create a custom sensor in the SAL layer, you specify the sensor as a custom protocol, and then you provide all the parameters along with the SO file that you just compiled. At this point, you will be able to ingest the data. You can see a few examples here of IMU, CAN, and GPS as to how you can specify the custom sensor type. These are the required APIs to successfully integrate a sensor into SAL. Most of these APIs are common across all sensors, like the lifecycle and playback. The data APIs, however, will be specialized to the sensor because of the sensor type-specific data structures. The plugin developer would implement these APIs in the plugin developer column and provide the shared object library file, and the application developer will consume the data using the APIs in the rightmost column. In the next few slides, I'll walk through the sequence of function calls so that everyone understands the flow in which these functions are called. The horizontal axis marks which layer the processing is occurring at. The live decoding sequence starts by the user application calling the DW_SAL create sensor, which accesses the sensor abstraction layer. Since this is a custom sensor, the SAL calls sensor type custom to create the sensor. Then within this constructor, we call the plugin function provided by the vendor library, which is DW_SENSOR_plugin_create sensor. After processing, sensor handle is returned all the way to the application level. The middle part of the diagram shows the sequence to start the sensor. Application calls DW_SENSOR_start with the provided handle, and that calls all the way to the vendor library, the DW_SENSOR_plugin_start function. Processing happens and the function returns all the way to the application, and the sensor is up and running. The last part is the reading and decoding of the data. App calls DW_SENSOR_xxx_read. The X's will represent the sensor type, so the 3 X's here will be replaced by lidar, for example. This returns a piece of decoded data to the application, but the complete sequence is to call redraw data. Here, that call is happening at the SAL level, which calls the redraw data of the custom sensor, which subsequently calls the underlying plugin function. The DW sensor plugin underscore redraw data returns a piece of data to the SAL layer. Because we can't assume that the payload from one redraw data call will be sufficient to construct a message, we have a dispatch call to continuously push data and then decode. Once we get enough data to decode, we call process data buffer in SAL, which calls the corresponding function in the plugin. This decodes the raw payload into, say, a point cloud or radar detection, and then it gets returned to the SAL, and from the SAL to the application. The live recording sequence is the same up to the point where we call the serializer. Once we have the raw data, it goes all the way to the serializer layer to write to disk. We also update the seek table that the sensor contains, which is update index table. The call to process buffer data during the decode use case is to be able to get the information to populate the index table. This contains the timestamp and data offset for each decoded message. This step is for IMU and CAN sensors in particular. In case of radar and lidar, the processed buffer data step does not occur. Here, we're showing the playback sequence for a virtual sensor. The create sensor is simpler, as it just needs to open a file. This does not need anything from the plugin SO file during creation or starting, so all happens at the sensor type virtual layer. Start just creates a thread to fetch data from the file and fill the FIFOs. Reading is similar to the other sequence diagrams, but the data is fed by a sensor type virtual layer, not the plugin.so file. Here, we're dealing with a virtual sensor, so no transport layer is needed. We follow the same sequence of redraw data, dispatch, and push data to get the data in, and then call the process data buffer to decode. The plugin library is used for these two cases, push data and process data buffer. Today for the demo section, I would like to walk you through the plugin implementation for a Cepton lidar. The device we will be using is a Cepton Vista lidar with a 60 by 24 degree field of view. I will walk you through the code snippets of the required APIs I wrote for this plugin. First, we will go over the lifecycle APIs. Create handle is the function that instantiates the sensor object and returns the handle to the sensor. This function should perform necessary memory allocation to hold the context information for a sensor instance. The create handle is passed back to the plugin on each subsequent function call. The memory allocated by this function should be allocated on a future release call. It's important to note that a user may create multiple sensor instances within a single plugin. This notion of a context or a handle is helpful for supporting multiple sensor use cases. The create sensor function is only called in the case of live sensor operation. This function should perform all necessary groundwork to start the sensor. In case of our implementation, this function only performs basic parameter parsing. As this is a TCP or IP sensor, we hold off on opening the IP socket until the start method to ensure stale data doesn't build up in the socket buffer. The release function shall deallocate and release any resources acquired during the create handle and create sensor calls. For the case of Cepton, we stop the sensor if not already stopped and delete the sensor instance. Now, we're going to look at the start, stop, and reset functions. The implementation of the start entry point is dependent on sensor and the implementer. In our sample plugin, we choose to defer socket connection and bind to this point as it reduces any stale data residing in the kernel socket buffer. After a call to start, the sensor plugin should be ready to serve up data from the sensor. The stop implementation should perform the opposite functionality of start. In our case, this results in us tearing down the socket connection with the device. Reset function similarly and results in us tearing down and bringing up the communication channel with the Cepton device. Now, we jump into the data APIs implementation, read raw data, return raw data, and push data. The read raw data entry point is where the plugin queries the sensor for new data messages and returns the raw bytes of data to SAL. The implementation should be prepared to allow multiple raw buffers in flight at a time. Our sample plugin implementation provides a reference buffer pool class that can achieve this. In our implementation, we're first copying the metadata, which is a size followed by timestamp, and then populate the raw data. After collecting the raw data buffers from the read raw data API, SAL will call push data inside the plugin. The push data function gives us the capability to collect the raw data into a buffer when a single sensor message doesn't translate to a decoded message. In our implementation, we push the received bytes to the Cepton SDK that will perform decoding for us. The return raw data entry point returns the raw data pointer to the plugin that was previously acquired through the read raw data API. The parse data buffer is responsible for using the push data and decoding the raw bytes into the DriveWorks data structure. Now that we've seen how to write the required APIs, let's cross-compile, move the shared object file to the target, and replay the sensor. I pre-recorded this part following the development cycle Hope mentioned in the earlier slides. I cross-compile on a host system running Ubuntu 16.04 and transfer the file over to a Drive Ajax system running the Drive Software 9 release. I also connected a Cepton lidar to the Ajax system for the replay.
So currently we're in the user local DriveWorks samples build directory. This is where all our build files are going to reside. We have our plugin source code in sample source sensors plugins, and it's in a folder called lidar_ext. So all the code that I've shown you is in that folder. I actually have a script written for cross compilation, and that's called build_arc64. So let's see what's in there. So I'm specifying that my build type is a release. I'm pointing to the right toolchain file. And the last one is where I pointed to the Vibrante PDK string, and this is where all our cross-compilation libraries reside. So when you set up your host environment, this will all be set up for you. So let's go ahead and run this script, and we see that a whole bunch of text has been written. Let's go through that. So we see that it's cross-compiling for Vibrante, and we also see that the DriveWorks samples install directory is written, and all the build files have been written to the build directory as well. So let's see what the build files are, and we're going to go to the install directory, and because ours is a shared object library file, it's going to be in the lib folder, and that is going to be libsample lidar plugin ext.so. So let's copy this file over to our target machine. I have the IP address memorized. So it's going to be NVIDIA at 10.110.51.30, and I'm just going to put it in the home folder. So we see that the file has been written to the target. So now let's switch over to the target machine. As you can see, we're in the Drive development platform Xavier A. I'm currently connected to Xavier A as it shows. We copied over the sample file to the home of the Xavier A, so let's see, it's there. Let's move that over to the correct location, which is going to be user local DriveWorks and bin. The reason I moved it there is because all our lidar replay samples are in that folder already, as you can see. So now we have the lidar plugin ext.so there as well. So let's go ahead and run that file. In my new terminal, I'm going to just hit the up arrow to get the command out. As you can see, I'm giving it the IP address the lidar is connected to because this is a live sensor, and the port where it's transmitting the data. The decoder path is going to point to the plugin ext.so file that we just created. So let's go ahead and hit enter, and as you can see, it's running. This is not a very exciting view, it's just my cubes and people just walking around. As you can see, you can pan and zoom the video as well to see different directions. We've seen how to run a live sensor. Now let's see how to replay a virtual sensor. I actually recorded a file earlier and put it in data samples sensors lidar custom.bin file. So I'm going to give the file path and then the path to the same plugin ext.sl that we just created. And I'm going to hit enter. As you can see, the lidar replay sample is running from a file. This is also a picture of my cubes that I've done a while ago.
To summarize, in this demo section, we covered how to implement a plugin, cross-compile the plugin for the target machine, and we also saw how to replay a live sensor and a virtual sensor with the newly compiled plugin. I would now like to pass it back to Hope to wrap up this webinar and open up the session for question and answers.
Thanks, Aradia, for that detailed overview of the DriveWorks sensor abstraction layer and the sensor plugins. To summarize, the DriveWorks sensor plugin framework allows the developer to implement both the data transport and decoding layers, providing total control and customizability of the sensor integration. And the DriveWorks custom camera feature enables integration of GMSL-based image sensors into the Drive software stack. The custom camera feature and the sensor plugin framework for LiDAR and IMU sensors are available today with the DriveWorks that is bundled in Drive Software 9. The next Drive software release, anticipated for later this year, will include support for radar, GNSS, and CAN-based sensor plugins. Once you get started developing sensor plugins with the DriveWorks SDK, here are the next steps. If you are not already part of our Drive developer program for Drive AGX, the first step is to contact your NVIDIA account manager to get started. And if you don't know who your NVIDIA account manager is, simply send us an email at the address mentioned here, and we'll assist you. Once you are part of the Drive Developers Program, I encourage you to review the Drive software documentation on our Drive DevZone site, which can be found at developer.nvidia.com/drive. The software documentation includes a complete DriveWorks SDK reference guide that describes the APIs and workflows for the topics we discussed today. While you are on our DevZone site, you can download the NVIDIA SDK Manager and install Drive software, including DriveWorks, on your Linux PC. Our SDK Manager walks you through the process and install DriveWorks on your computer for you, so you can just get started with development. Once the SDK is installed, I recommend you compile and review the DriveWorks samples, which are fully functional demonstrations of DriveWorks capabilities. We provide the source code for the samples, making them a great starting point for your development. After familiarizing yourself with DriveWorks, it is on to developing your sensor plugin using the steps we covered in this webinar. Once you have successfully integrated and tested your sensor plugin on the Drive platform, contact us and we can add your sensor plugin to our catalog for all developers in the Drive ecosystem to access and use. We will also feature your plugin on NVIDIA's automotive partner page. And that's about it. We'll be happy to take questions from the audience.